Is PA3 still out? I don't think code reviews this week, so I guess you'll get those 10 points later on from something else, but I don't think attending recitation this week counts towards that. Yeah, the professor didn't really tell us anything about code review yet, so I think it'll be later on. And okay, so let's get started. And wait, why did it just change on its own? Okay, so today we're going to be covering assembly, and we're going to be talking about condition codes and if statements, loops, and functions in assembly. And then if you guys have any questions about Bomb Lab, I could answer those. So the grades for programming assignment 3 are out, and Prince and Marie were the graders. So if you have any questions, you could go talk to them. And PA4 Bomb Lab is due next Tuesday. So you guys have a week from today to finish it. And yeah, so how's that going for everyone? How, did you guys start Bomb Lab? Oh, really? Yeah. Oh yeah, phase 6 is a tough one. Yeah, you just gotta, I mean, hopefully the stuff we go over for assembly today will help. And then, yeah, you just gotta use those GDB commands and try to figure out what's going on. And definitely come to office hours. So we could help a lot there too. Okay, yeah, so when a program is running in assembly, there's different things that we need to keep track of. And so different registers have different purposes. A lot of them are general purpose, but there are also specific ones. And so we have RAX stores our return value for the function that's running, and we'll talk more about that later. But yeah, so we'll get into what all of this stuff on this slide means as we go through the lecture. But so the register RSP will store the top of the stack, and RIP will store the instruction pointer. And then we also have these 4 condition codes, which are useful for just seeing the result of comparisons. And yeah, so these are our 4 condition codes. They're single bit registers, and it's either a 0 or a 1. It just turns on or off. And so you have carry flag, 0 flag, sign flag, and overflow flag. And so here, so all of these flags are implicitly set. So it's kind of a side effect of the arithmetic operations that happen. So if we did the addition of 2 numbers in the source and destination, these flags will be set for, it'll check if the resulting number is equal to 0. So if you add source to your destination, it'll check the value in the destination after. And if that turns out to be 0, then the 0 flag will be set. And if that value is negative, then the sign flag will be set to 1. And if it's positive, it'll be set to 0. And then there's also flags for overflow and carry, but we don't really need to know much about those. But yeah, so just know that those are also different flags that you could check. And the only time flags, or one of the times that flags aren't set implicitly, is when using the Leah instruction. So when you pass anything into that, it doesn't actually set any flags. And then we have So we saw here that flags are set implicitly as you do any sort of operation, but you could also explicitly set them by using the compare instruction. So we have the CMP instruction. It takes two source values and it compares them. So doing the comparison of B and A is like doing A minus B, but the result doesn't actually get stored anywhere. So it'll do A minus B and it'll set the flags accordingly. So let's say if your A and B are both 5, it'll do 5 minus 5, you'll get 0, and then the 0 flag will be set. And so yeah, basically if A and B are the same thing, the 0 flag gets set. And so these are just, when you use CMPQ, it doesn't actually store the value anywhere. You're deliberately setting flags that you could check later. And you could also explicitly set these flags using the test instruction. So it takes similar arguments as the compare instruction, but what this does is A and B. So it's basically just it's comparing the two numbers bit by bit. And so the 0 flag will be set when A and B is equal to 0. And the sign flag will be set when A ANDed with B is less than 0. And so then we also have the set instructions, which set, so you could basically take your take the values in the 0 flag or the sign flag, and you could store them somewhere. So let's say you want to compare if two things are equal, and then you want to take the result of that comparison and store it in a different register. And that's what this can be useful for. So our registers are way bigger than the single bit that the 0 flag or the carry flag need. And so all it does is it alters the lowermost byte, which is the first 4 bits. It only alters, it basically just alters the first bit and sets it to 0 or 1 based on the condition codes, right? So if we did something like set E, um, it'll check the value of the 0 flag at that moment. And if that value is 0, it'll set your register to 0, and if it's 1, it'll set it to something else. It'll set it to 1. And yeah, so we have these integer registers, remember? And you can also recall that we discussed how you could access different parts of these registers. So you could access the lowermost part, or the single byte out of the 8 bytes of the register, by using these symbols here. And so that's how we can access that actual what the flag is set to after the set instruction is run. So basically what we do is so it okay so what set does is it just sets the lowest order byte. So that's all we need to pass to it. So we saw that for RAX, the lowest order byte was AL. So we could see in this example code that AL is the input that it takes. And it'll set AL when RSI is greater than RDI. So okay, so let's take a look at this function, right? It's just GT greater than, so it takes a long X and a long Y, and it returns X is greater than Y. So it'll be true when X is greater than Y, false when it is less than or equal to. So basically let's translate this into assembly code now. And so let's say we have RDI storing argument X, we have RSI storing argument Y, and RAX will store our return value. And if that's the case, then we'll have this compare instruction. It'll compare RSI and RDI. And remember that the compare instruction explicitly sets our flags. So then what we do is we use the set G instruction, which does this operation, and that basically is equivalent to checking if it's greater than, and it stores the result of that in AL. So, and then AL could have possibly contained something else in the other 7 bytes um, that are not, or sorry, RAX could have contained something in these other 7 bytes, but all we modified here is AL. So we can use this move ZBL instruction to zero out the rest of RAX. So basically, all we tell move ZBL that we just want to keep what's in AL, and then the rest of RAX gets zeroed out. So when we check what's in RAX, it'll be either a 0 or a 1 based on the set G instruction, and then we just return. And yeah, and then we can also jump to different parts of our code, right? So we could so this JMP, it jumps unconditionally. So we could just say jump to multiply, and it'll jump to our multiply function. And JE will jump when the result of some comparison was equal. And so yeah, similarly, all of these different instructions jump when different flags are set. So then let's say we have this function here. So what this does is it just calculates. So it takes an x and a y, and it has a result variable. And if x is greater than y, it does result equals x minus y, else it does result equals y minus x. So it basically takes the absolute difference between the two numbers and doesn't account for negatives. So it basically just takes the difference and takes the absolute value. And then it returns the result. And then so this can be translated into the assembly code that we have here. And so we have x and y in, so we have x in RDI, we have y in RSI. So we compare x and y, and if x is, if it turns out that, well, we give it y and then x, and then if y is less than x, it will, or sorry, if y is, if x is less than y, it'll jump over to, or sorry, if x is less than or equal to y, that's what the LE means. It'll jump over to L4, and then what L4 will do is basically the equivalent of this this red part here. And otherwise, if x is not less than or equal to y, and that means x is greater than y, so we want to execute this. So it'll take x, move it into RAX, and it'll subtract y from whatever's in RAX, which is our x. So it'll do x minus y. And there's a reason that we took x and put it into RAX, and that's because RAX stores our return value. So the function that called absdiff expects the return value to be in RAX. So we need to store it in RAX before we return. And this does the same thing, but this instead does y minus x. So it moves y into RAX, subtracts x from y, and returns. And so we can think of translating between C code and assembly code as go-to code. So basically, let's transfer this the C code we just looked at into go-to code. So basically what this is doing is we have the same long result, and then we have a variable which is called n test, and that basically is set to 0 or 1 based on whether or not x is less than or equal to y. And if x is less than or equal to y, it'll be set to 1, otherwise it will be set to 0. And so if n test is true, it'll go straight to the else. So if x is less than or equal to y, it's the same thing here. We want to jump to the else. So if x is less than or equal to y, we go to the else and we do this. Otherwise, we'll just do this. It'll continue to execute the rest of these instructions. So we do result equals x minus y, and then we go to done, and done just returns our result. And then we have and then we translate the go-to code that we have into, or this conditional move code that we have, into assembly. So so what's happening here is, so we have RDI contains our argument x, RSI contains argument y, and RAX will be our return value by convention. And so first what we do is we move RDI into RAX. So we move x into RAX, and then we subtract y from x, and we have that result. And then we move y into another register RDX, and then we subtract x from y. So we do y minus x, and then we compare the two, x and y, and if it turns out that that it's less, so if it turns out that the result was negative, it'll actually move the result in, or sorry, yeah, it compares our original x and y, and if x was less than y, it'll move whatever's in RDX into the return register. So in this case, it'll return the result of y minus x. Otherwise, if this isn't true, it'll just go on and return whatever was already in RAX. And this line won't be executed at all. And then we have a do while loop. And so this is, I guess, the first time we're talking about loops in assembly. So let's try to transfer our C code of this do while into the go-to version. So what this does is it just takes a variable x, and it has a variable result, and it does some stuff. It doesn't really matter what it does in there. We're just trying to map the do while to the loop. So it does some stuff in here, and it does that while x is not equal to 0. So basically what we have here is we have this label for loop, and all of this code is inside that. So first, it does exactly what the do part does, and then it checks if x is not 0. So if x isn't 0, it'll go back to the loop. So it does exactly what this code does, but in a go-to fashion. And then what we can do is we could transfer this go-to version of the code into assembly. And so let's say our argument x is in the register RDI, and RAX contains a result. Then so then we could transfer this into assembly code. So what we do is this initially sets result to 0, right? So all we do is move 0 into EAX, which is our result value, which is the 32-bit half, or 32-bit half of our 64-bit register. And then we have a label called L2. And what this is doing is, so we move RDI into RDX. So we move our argument X into the register RDX. And then we AND it by 1, which is this line here, which basically just calculates this, which is what our code does. And then it adds that to result, which is also what our code does, but in one line. And then and then it runs a shift right on RDI, and that just shifts it right by 1, which is exactly what we did here. And so here now, if X is equal to 0 after the shift, then so remember how we said that these flags are implicitly set. So we didn't actually explicitly set the flag by doing this, but when this right shift is done, flags are set automatically. So when this right shift happens and X is the result of the right shift makes X equal to 0, then the 0 flag is set. Otherwise, the opposite is set. So then this JNE condition here, which stands for jump if not equal, checks the 0 flag. And if the 0 flag is set, it'll jump back to L2, and the 0 flag is set based on the previous instruction, which is what we just talked about. So this instruction sets the 0 flag implicitly, and this jumps if the 0 flag is set back to L2. Actually, it jumps if the 0 flag is not set. So if the result was not equal to 0, it jumps back into the loop. So this is a little this is wrong here. So if the 0 flag is not set, it'll jump back to L2, and then it'll just return. Yeah, so this is basically the general translation. You take your C code, transfer it to goto, and then you could take your goto and transfer that over to assembly. But yeah, this is the basic idea of it. So just take your while test, put it in an if, and if that condition's met, you go back up to your loop and the body's executed. And then this is a while translation. So if we have a while loop instead of a do while loop, this is how it would get translated to goto. So we have while test. So we have a while loop that executes a test and then executes the body. So initially, right as the function starts, it goes straight to test, which is exactly what happens in the while loop. So a do while loop would allow the body to run at least once, which is what do while is for. But in this case, the test is ran right from the start. So only if the condition is initially met will it go into the loop, and then it'll just execute the body, and then it'll do the test again and go back to the loop, and it'll keep doing this until the test fails and the function will end and return. So here's an example of translating this while loop into this goto version. So before we had this code as a do while, but now it's in a while. So it just checks that while X is true, it does all this, and that's it, it returns. So what our goto code does is it goes straight to test, and it does, if X is true, then it goes into the loop, does whatever happens in the loop, back to the test, checks it again. If it's true, goes back to the loop, and then goes back to the test. Once it fails, it'll return the result. And so this is the general while translation that we have. So we could also So this is another way of doing it. Instead of going straight from while to go to, we could actually go from while to do while, and then we could go from do while to go to, which might be easier in some cases. And so, and the reason we're doing all this is because going from C to assembly isn't that straightforward. We don't have for loops or while loops in assembly. So we need to take these different pathways in order to translate our code over to assembly. And yeah, so this is another way of doing it. So we take our while loop, which just runs a test, executes the body. And instead of that, we initially have an if condition where if the test condition is not met, it goes straight to done and the code ends, which is exactly what would happen in a while loop. And then other than that, it just does the body while the test condition is met. So here it initially just checks if the test condition isn't true, goes straight to done, and then so in this way we don't need another label just for the testing part of it the way we did here. We needed another label just for testing, but we don't need that anymore. The test happens as part of the loop body itself, sort of. And so this is another example, and this time it's done using this method. So we take our C code, same C code, does a while loop, checks if X is true, executes some code. So what's happening here is we did exactly what we established here. So we check if X is not true, and if it's not, we go straight to done. And then, but if it is true, it'll go into the loop and it'll do whatever the loop does. And if X is true, it'll go back into the loop and keep doing that until X becomes false. And then we also have for loops, right? So basically the best way or the easiest way for us to understand for loops being converted into assembly is first let's convert the for loop into a while loop, which is not that hard to do. You just take your initial condition, you initialize it up here, and you take your test and put it in the parameter to the while loop, and you do your update after the body executes in the while loop. And then we already went over how while loops can then be translated into assembly in this example here. And then, yeah, so you could also then translate your while loop into a do while loop and then go to assembly. And then we could talk about functions. So now that we've covered loops, we have our base to go into functions. And so before we go into how functions are written in assembly, we can talk about the stack a little. So so in memory, the stack grows downward. So basically, so the top is actually down here. This is the bottom of the stack, and in memory, the stack grows downwards and the heap grows upwards. And basically, you run out of memory when the stack and heap kind of meet in the middle, and there's no more memory left for you to do anything with. So yeah, it grows toward the lower addresses, which is the same thing as saying it grows lower or grows towards the bottom of memory. And our register RSP is going to contain the lowest stack address, which is effectively the top of the stack. So our stack pointer here initially points to the top of the stack here. And let's say we want to push something onto the stack. We have this push operation. It takes a source and just pushes it onto the stack. And what we need to do in order to push something is take RSP and decrement it by 8. So So basically, we want to move over to the next location in memory. And in order to do that, we take RSP and move it down by 8. And so RSP, instead of pointing over here, now points here to this new location. And the reason we're decreasing is because it grows down. Remember, it grows, the stack grows toward lower addresses. So going down creates more stack. And then you take your operand and write it to whatever is whatever RSP points to. And that's how you basically push something onto the stack. And then RSP now points to the top of the stack, which is the new operand you just pushed. And then pop is very similar, but it does things the other way around. So you basically read the value at the address given by RSP, because pop always returns what it popped. And then we take our RSP and we just increment it by 8. So when RSP now points up here instead of at the value that was pushed onto the stack, that value is effectively popped off the stack, because RSP is the pointer to the top of the stack, and it's no longer pointing to that value. So now that value is popped because we moved RSP back up by 8, and the value that we read is stored in some destination register, because pop stores whatever value was popped, and then you could access it as a programmer. And so here's some example code. So we have this code multstore. It takes X, Y, and a pointer to a destination. And so what it does is it calls this other function called mult2. So this function basically just stores the result of the multiplication into destination. And it calls this function mult2 to actually do the multiplication. It passes in X and Y and multiplies them, returns them. And then we take, and then we dereference destination and store the value of T in it. So the multiplied total. And so to do this in assembly, what we do is we first push RBX onto our stack, and then we move our RDX, which is the destination, onto into RBX. So you're basically saving whatever was initially in the destination into RBX. And we'll come back to why we do this. And you'll understand it once we go through more stuff. But basically, it then calls mult2, and it goes in here, and it moves RDI into RAX, and then that basically takes the value in A and puts it into, and it knows that A will be in RDI, and you'll understand why that is, but it basically moves A into RAX, multiplies them, and returns them. And we know RAX is the return value, so that's what was returned. And then you move RAX into RBX because we want to put it into the destination, and then you could pop RBX back and return. So basically, this procedure control flow in assembly, it is what we're talking about here, and the stack is used to support function call and return. And we know that because whenever a function is called, the stack frame is generated, and that's where all of the local function things are stored. So basically, we have our procedure call, which is you just use the call instruction and pass it a label. And what that does is it'll push the return address onto the stack. And because once you call a function, after the function is done executing, you need to know where to go back, right? And execute the rest of the lines. So it pushes the return address onto the stack, and then it jumps over to the label. And then, so the return address is the address of the next instruction right after this call. And and then you just return it. And what return does is it pops that address off of the stack and jumps to that address, that return address. So here's an example. So we know that RSP is our stack pointer. So it initially holds the address of the top of the stack. And RIP is the instruction pointer, which initially points to this call queue instruction, right? Which is 400, 544. And then, or we're not going to worry about the stuff it does in the middle and before and after here. We'll just focus on these parts. And then, so and then the instruction pointer moves to the first instruction in mult2 because the function was called and all of this execution mult2 is happening. And RSP, so when we entered the function call, the return value got pushed onto the top of the stack, right? The return value is 400, 549 because this is where we want to come back after mult2 is done being called. So that's now on the top of the stack and RSP is pointing to that. And then the instruction pointer moves over to the return as it executes this mult2 function. And then the return instruction pops the return address off of the stack. And we see that it's no longer there. And the control flow returns to mult store. And the instruction pointer now points to the return address that was popped off. So the return address was this. And the instruction pointer now points back to that return address. Okay, and then we have this. So basically, this is where we talk about convention. And this is the reason we did everything we did in this slide that we saw before. So basically, we have the first 6 arguments of the functions that are being called by convention are stored in these registers. So argument 1 is stored in RDI, and argument 2, 3, 4, and 5, and argument 6 is stored in R9. So when a function is called, it'll know that that's the order that the arguments are stored in. And then we also have our return value, which is register RAX, and RIP is the instruction pointer register. So these are kind of our special registers that you need to be mindful of when you read assembly code, and it'll help you understand what's going on a lot better. And yeah, so after the first 6 arguments, the rest of the arguments are all just stored on the stack, and they're not stored in registers. And so basically, we really only need 6, like you won't really have more than 6 arguments in a function most of the time. So space is only allocated when needed on the stack. Otherwise, they're just stored in the registers. And so let's go over this data flow example from before again. So we have our, this is the C code, and we know that all this does is multiplies 2 numbers and stores it in a destination. So we have our value X in RDI, we have Y in RSI, and we have our destination in RDX, right? So what we're doing initially is we're moving our destination into RBX to store the value of the destination, and then we have our call to mult2, and mult2 is called, and also so we know that whatever function called mult store followed the convention of putting the first argument in RDI, the second argument in RSI, and third argument in RDX. So that's why our function was able to continue this way. And yeah, so it then calls mult2. So let's go into mult2. What does that do? So the X and Y are already in the right place for mult2 because we know that the first argument is in RDI, the second is in RSI from convention here. And so mult2 straight up goes and looks into those registers, and we don't actually need to move X and Y into the correct place so that it knows where they are. they're already stored in there, and this is a convenient side effect. So we can move our value A into the return register, multiply the value of A by B, and that multiplication is stored in the return register RAX, and then we return it, and then we just do this last part, which moves the return value that we got, which is in RAX now, into RBX. So we dereference RBX, which is exactly what's happening here, and we move the value from RAX into our destination. And so that's basically how data flow works in assembly and how functions kind of interact with each other. It's more complicated than there are more complications, but this is the overview of how it happens. And yeah, that's all I have for today for you guys. So you guys are free to leave now if you need to. So we ended 10 minutes early, and now if you have any questions, you could stick around and ask. Yeah, no problem. You're welcome. And I will stop the recording now. And I'll have the recording up by tonight. And I'll also post this presentation on Canvas.